we have Sai Krishna Revanth VARUMA, who is a doctoral candidate in computer science at the University of South Carolina.
Welcome everyone. I'm Sai. I'm a doctoral candidate at the University of South Carolina. And this is the work that we did over the summer of 2023, where we just evaluated multiple generative AI models to see how they would perform in low resource design challenges and how they would perform with added constraints. All right. So first of all, the actual motivation for the work that we did. Generative AI, as we know, has been on the rise lately. Ever since ChatGPT came out, it's pretty much the buzzword. You have to be in Gen AI, or otherwise you're not even up to the mark. But what happens with most of these Gen AI solutions is that they're heavily dependent on cloud computing, and they require large computing infrastructure to actually be able to deliver the service that they want to deliver. And some of the situations that we seek to address are where users in like rural, disadvantaged, or special situations where they don't have the same level of resources or the access to those resources to be able to effectively use generative AI to deal with situations that occur at a local level. And where we feel that TinyML could come in is that this area has long been working in the making and congesting or basically zipping up machine learning models to make them more easier to interact with, and also be easily available for offline and compact models. And why these models could also help, as I was mentioning previously, there's limited connectivity in these areas, and they have significant computational constraints, which just traditional models cannot address. And there's also a lack of literacy with using these models that just people in those areas don't have access to. One specific design case that we were looking at is engineering design problems. So let's say you want to design a water pump for your use case, or it could be a pen, it could be a bicycle, whatever suits you. But for the model to be able to make an accurate prediction to your use case, it needs to have local understanding of the situations in your domain. For example, your locality may not have cement roads, your locality may have muddy roads, for example. So if for your model is trying to design a bicycle, it should take that into account before making any suggestions or design recommendations to you. Looking at the current models that we have out there in terms of GenAI, large language models like your ChatGPT, your Gemini, your Cloud, etc., they have shown remarkable performance in natural language generation and understanding. But however, most of them usually only deal with text modalities, so they don't quite fit the case for design. Then there's diffusion models, your stable diffusion XL, and so on. So they can actually generate high quality images from text prompts, but they do require quite significant prompt tuning and prompt engineering to be able to give you reliable and efficient results. Which brings us on to vision language models, such as your Flamingo, your maybe Cody to an extent. So these models actually do have and do facilitate human-like natural conversation. So you can give the model feedback on what you don't like in its previous output and what you want it to change. But another issue still remains is that the way that these models are trained, you still need to be doing a lot of prompt engineering, and there needs to be a in-detail understanding of what the model does and cannot do to be able to actually get good results out of it. Then there's multimodal LLMs, Cody, Order, and so on. So these models, with the way they're trained, and recently ImageBind, so these models with the way they're trained, they have understandings between the embeddings of text, audio, video, and other forms of input. So they present a more exciting opportunity and potentially may have a more in-depth understanding of design cases, just to the fact that they're trained on a much larger corpus. So they do have understanding of design or engineering design at some level. And one of the recent studies that was conducted using GPT-4 actually proves that point, that the model was actually able to understand and give you good ideas based off of just text prompts. Okay, so that brings us on to the key point of my presentation, which is using generative AI for local design. So consider two use cases. So the first would be predicting potential impacts, as I mentioned previously. So the model should be able to understand what that design or what that product means for your community. So if you're designing, for example, a wooden stove that could be used in rural areas, so the model should be able to understand and gauge the impact that that product could make on your community and your way of life. Without this understanding, which usually is lacking in most of our models, they are not able to make significant impact and are hence shunned away by that population just because it's not addressing their needs. Another use case would be product design and repair. Building on the bicycle example that I gave you earlier, a more local case could be, for example, a water pump. If your water pump has stopped working and you have access to, let's say, local generative AI models, you can actually show the model what the condition of your pump looks like and ask it suggestions for this pump's not working. Could you design a valve for me using these materials? You can also tell it, design a greenhouse for me that's just made of wood or maybe made of plastic. So you're giving the model constraints on not only the design of the product, but also what material you're using for the product. So the model should be able to understand that, for example, wood can do certain things that steel cannot. And similarly, steel can do certain things that plastic cannot. So your model needs to have in-depth understanding of both materials and design to be able to effectively recommend solutions for local design cases. So some potential solutions that we hypothesize could be useful in this domain is model compression and optimization. There's a lot of techniques such as pruning and knowledge distillation, for example, using which you can actually make your large language models or multimodal LLMs smaller. So they can be, I mean, this is looking way ahead into the future, but they can theoretically be just available on your phone as an app. And using that app, you can, create solutions for local design. Then there's edge computing or neuromorphic computing as well. So processing data closer to the device instead of doing it on a cloud would also be a crucial factor in realizing generative AI for local design. Then another important factor is evaluation metrics. So usually we evaluate our models on precision, accuracy, recall, the usual ML metrics. But when you're trying to generate something for local design, I think what's also important is seeing how well the model is adapting to the constraints that you put on it and how realistic its solutions are with respect to the constraints that you give it. So in conclusion, we hypothesize that using concepts like TinyML, Edge AI, and neuromorphic computing, we can make our multimodal LLMs and machine learning models more smaller. So that way they're more accessible to a larger population, and they also provide effective solutions for local design. So as I mentioned earlier, this was part of a position paper that we put up in the summer of 2023. It was published recently in the AI for Design Bridge program at AAAI 24. So I would invite you all to go ahead and read the paper. So this is a precursor to a much larger set of experiments that we will be conducting in the coming months. We hope to expand on the study that we did in the summer and obviously get some actual results and maybe even some images that we can use for presentations and so forth. So yeah, thank you. If you have any questions, I'm happy to answer them. And if you want to know more about our lab and the work that we do, you can do so by scanning the QR code here.
Thank you very much for your excellent presentation. Huge thanks to all of our partners. Wouldn't be possible without you. We have AI Zip, Arduino, ARM, BrainChip, Edge Impulse, which is where I work, Embed UR, Efficient, Greenwaves Technologies, Gravetti Inc., Hymax, ImagineMob, Infineon, Inotera, Nota AI, NXP, P&G, Corvo, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, ST, Synaptics, Sentient, and TDK. These are our strategic partners. We also have executive strategic partners, Qualcomm AI Research, who are advancing AI research to make efficient AI ubiquitous, Sentient, who are accelerating your edge compute, making edge AI a reality, And our platinum strategic partners, Embed UR, Atrios, who deploy Vision AI at the edge at scale with Sony. And our gold strategic partners, Arm, building the future of TinyML, Edge Impulse, the leading development platform for Edge ML, Infineon, driving decarbonization and digitalization together, and Renesas, who are enabling the next generation of AI-powered solutions that will revolutionize every industry sector. ST Microelectronics, who provide extensive solutions to make tiny machine learning easy. Synaptics, who are engineering exceptional experiences. And our silver strategic partners, AIZip, Arduino, BrainChip, Efficient, Greenwaves, Gravetti, HiMax, Imagimob, Inotera, Nota AI, NXP, P&G, Schneider Electric, SensiML, Silicon Labs, and TDK. Thank you to all of you. And that's to wrap up our session here. Huge thanks to the audience and all of the presenters. We've had an amazing couple of days of insights and inspiration to go forward and build great things. So thank you so much, everybody, again, and I hope you enjoyed it.